Thank you. So, okay, my work is about localization of fermions on technique grains. And that background is the place where I work. So the outline should be something like introduction, then give you a brief of brainwork and gravity, and what I do after all this localization of fermions. So let's begin. The motivation of this study is that the brains, which appear in string theory, are an important part of the ADS-CFT correspondence, and also they may solve the hierarchy problem. Okay? You can also use it like a kind of compactification besides the Calusa-Klein one known from the early 20s. And, well, they provide a natural way of identifying different chiralities of the fermions. And of course, I think so, they would be, if they exist, they would be the most natural phenomenological result of string theory. Okay. The Randall syndrome models were they found that gravity on the brains could be modeled just like a Newtonian gravity, even if you begin with a 5-dimensional theory of general relativity. They do two models. The first one was with a setup of two brains, parallel deep brains, and they found that this setup could solve the hierarchy problem because the 4-dimensional Planck scale could be much larger than the Witten scale, but the 5-dimensional Planck scale could be of order 1 TeV. The second model of Randall syndrome, they consider just one D brain, and they proved that, in fact, the induced gravity on the brain is just a 4-dimensional gravity. It behaves like 1 over r, and not like 1 over r squared. Soon after the Randall syndrome scenarios were introduced, so people tried to generalize these models, and one of the generalization was to find a domain wall whose domain wall had a thickness whose limit, yes, where the thickness goes to 0, give you just the same result as the brain of Randall syndrome. And it was found that this brain domain walls also localize gravity, but even more, because on this domain walls, one can also localize fermions. So, if you can localize gravity, the natural extension is to ask yourself what happened with matter. And the early stages of the theory, people asked the matter to be localized, but just imposed. It is like a 4-dimensional Dirac delta accompanied by the Lagrangian of matter. So there is no natural localization of fermions in Randall syndrome scenarios, and so we need to generalize this by one of the possibilities is adding new interactions. So the first interaction considered was adding a Chicago-like interaction. the scalar field is the scalar field who models the framework. Okay. And so you just have a 5-dimensional fermion, and we introduce a new parameter. It's the mass of the 5-dimensional fermion. Here I'll try to describe how to proceed, but my time is over. So if you have some questions, you should ask me later, or, well, this is how to proceed. And what we are actually doing is considering generalizations of the Yukawa coupling, like shown there, the two fermions and whatever power of the scalar field. And a curiosity is that we could find a solution for those kind of interaction even when the exponent of the phi scalar is negative. So, I think I should finish here. Any questions?
Yeah. To localize range fields too?
It is possible to do it, but we are not doing it right now. We are just trying to, well, this is not the last state of the work, but we analyze the modular space parameters that aim for 5-dimensional M and another parameter that is introduced somehow. I couldn't describe it. So one can find a region of the modular space where the fermions are localized. And so after that, we want to move on to gauge it and see if it's possible that in the same region of parameter